Welcome to this short film about fire safety in the engine room. The film has been made by DNV with the purpose of raising awareness around the fire hazards in engine rooms. It is a known fact that in order to start a fire, there are three factors that have to be present: heat, fuel, and oxygen. The engine room contains all three. Heat, represented by hot surfaces. Fuel, represented by flammable material and liquids. And of course, oxygen. The challenge is, as everywhere, to keep these three items separated. One main focus in both the DNV rules and the SOLAS Convention is to remove the heat in the fire triangle by properly insulating all hot surfaces in the engine room, as one of the most common reasons for fires in the engine room is flammable oil hitting hot surfaces. It is not too difficult to generally establish the areas that should be properly insulated. The challenge is to make sure the insulation covers everything. In cases where the insulation is insufficient, so-called hotspots will occur. Any such hotspot represents an immediate hazard in case it is hit by an oil spray. Examples of well-known hotspots are typically, but not limited to, indicator valves, cutouts for pressure, temperature sensors, cylinder covers, the exhaust pipe from each cylinder, the transition into the exhaust manifold. The exhaust manifold in particular overlaps between steel sheets and laggings. Turbochargers, in particular flanges, uncooled gas casing and uptake, turbo casings, boiler casings, and steam piping. Another main focus for preventing engine room fires is to make sure any possible oil sprays from leaking oil pipes are not hitting any hotspots. In addition to insulating the hotspots, it is also necessary to install some kind of screening around the areas where oil leakages may occur. Oil leakages may typically occur in pipe flanges and pipe fittings such as, for example, level gauges and flexible bellows. An oil spray of several meters may be created even in low-pressure systems, and the screening should be made in such a way that it prevents such oil sprays. The screening can either be made of tin plates as an enclosure, or it can be made of special screening tape. For high-pressure fuel oil pipes, the DNV rules and the SOLAS Convention are requiring that they are double-walled or jacketed. This means that any possible leakage shall be contained inside the pipes, lead to a separate tank, and give an alarm. It is important that the crew on board are aware of the importance of keeping this system in good working condition. The general attitude and awareness of the crew working in the engine room every day may in many cases be the tipping point with regards to the fire hazard in their engine room. A clean and tidy engine room represents a smaller fire hazard than a dirty engine room, so it is important for crew members to keep a high focus on general cleanliness in addition to the main points, as demonstrated in this film. We hope this brief reminder of how fire hazards in the engine room may be controlled was useful for you.
More vessel fires occur in port than at sea, but the majority of fires on board a vessel occur in the engine room, and the majority of engine room fires occur from oil leaking onto a hot surface. So if we can reduce these, we can significantly reduce the impact of fire on our ship. And we're going to concentrate and focus on engine room fires predominantly, but we're also going to do a little bit more of revision on fire systems and look at fire detection as well. So the means that we have of extinguishing a fire on board are with portable extinguishers, and we'll just do a quick review on those. Our fire main, we'll have a little bit of a talk about that, and our fixed fire extinguishing system. First up, let's have a quick look at our portable extinguishers, and we're sort of going to tie that into our classes of fire on a vessel. Well, our class of fire. So we have A, B, C, D, E and F class fires. Alright, so hopefully this is going to be an easy review for you. You should hopefully recall all of these. E is easy, that's electrical. And F for cooking fats and oils. Our D is for metals. We're not really going to discuss that in much detail. It's a specialist field. Our A class fires, that is our ordinary combustibles, our textiles, cardboard, paper, etc. B is flammable liquids. C is flammable gases. So just going to review quickly the best extinguisher to use for each of these type of classes of fire. So our A class, we're going to use water. And what colour is water? It is red band. Alright, our B class, our flammable liquids. What's the best type of extinguisher for this class of fire? I'm hoping that you said foam. And what colour is it? It is indeed blue. Alright, our flammable gases. The best way to fight a gas fire is to isolate, and then we've got a different type of fire. Same with our electrical. We can isolate the electrical component of it, becomes a different class of fire. So our best is to isolate it with an isolation valve if we can. But aside from that, our dry powder works quite well against a C class fire, and that is a white band. Metals, as I said, we won't go into. Our electrical, hopefully isolate, but if not, we can use dry powder. A better extinguisher is CO2, and that is a black band. The best type of extinguisher for our fats and oil fires, our cooking fats, is a wet chemical extinguisher, and this is oatmeal in colour. Fire main refers to the piping that allows us to pump water to our fire hoses, and normally seawater in a seawater environment. That consists of our hydrants, which are basically the valve that we connect our fire hose to, and then we have hoses and nozzles. Basically, depends on the survey requirement, but often we're required to have two independent means of pressurising our fire main. And essentially, the basic requirement, as I said, they can differ, but we should be able to reach every part of the vessel with a minimum of two hoses. We should be able to reach with our fire pressure. And essentially, our vessel is tested so that at the highest place we should have a decent amount of pressure with our fire hose. And look, again, it depends on the survey requirement, but commonly what is required is 6 bar pressure at the highest point. And then we might be required to have an emergency fire pump. So have our main fire pump located in the engine room, supplying our fire main, but depending on survey requirement, we can be required to have an emergency fire pump, and it has to be in a different source to our main fire pump, and normally it's driven by a diesel engine. Now we do have a fire main isolation valve, which we'll talk about in a short video in a little while. Okay, we have 2 C suctions on this vessel, one port, one starboard. In the engine room we're situated, this is the aft engine room bulkhead, and one of our C suctions on the port side is this one. So this is our C suction valve here, comes through to our C strainer. It's got 4 dogs on it, and then we've also got a butterfly valve, and yeah, there's 2 C suctions, port and starboard, and they both link.
we have a supply from our seawater to our fire main. So here's our fire pump, which is supplying the pressure for our fire main, the main fire pump. So the suction is up through this valve. As being a centrifugal pump, suction's always through the centre. It's driven by a three-phase electric motor via a coupling, and this is giving its output up through here. We've got supply to the fire mains within the engine room, and then a hydrant here, and then we've got our pipe going up to deck, and we'll have a look at that in a moment, where it comes out. It comes from our fire pump in the engine room, comes up through the deck to this valve, and from here it branches and goes forward, and that supplies all of our hydrants going up all of the decks, all the way to the wheelhouse, the bridge deck, and then it also branches off here and joins all the way along. We just passed a hydrant, and you can see if we follow it all the way through, and it goes down through a deck penetration there into and combines at the end down here with our emergency fire pump down below. So as it goes down through the deck, and we'll catch it on the other side.
Our emergency fire pump, little 3-cylinder Yanmar diesel, also a self-priming stalker pump. So if we have a fire in the engine room, we can come down here. If we lose power, we can come down here, start our emergency fire pump and use all our hydrants. So to start with, we have 5 valves we need to open. This is our sea suction. Our main sea strainer is down in our gear hold. So the pipe comes up through the strainer to this one. So we open our sea suction to our pump, and our discharge from our pump is valve number 2. Around this side, we have valve number 3, which is engine cooling. Now, this engine is raw water cooled, so we need to supply some seawater to run through our heat exchanger. So it's a matter of opening this valve here, and this comes from the outlet of our fire pump. Okay. Also, we have a valve for our exhaust, number 5, and number 4, most importantly, some fuel. On the bottom of our little tank there. It's obviously got a standalone tank. Exhaust. Okay, so every time that we go to sea, this engine must be right to start. Coolant must always be right, and obviously our oil level must be right. So that's how it's left. Alright, so because we're in a bit of a cold climate, we normally preheat our little Yanmar. We'll give him some heat until the heat light goes out, and then we'll try and start him.
Our seawater for the fire main passes through the deck into this valve. This valve plays an important role. It's called our fire main isolation valve. Now, we've got our 2 pumps, our emergency fire pump and our main fire pump down below, and they have to be in different locations. So we've got one in the engine room, one outside of the engine room. They both combine and meet up at this junction point at the fire main isolation valve. So the purpose of this valve is, if we have a fire in the engine room, we probably won't be operating our main fire pump in the engine room in that instance, so we can use the emergency fire pump. But if the fire gets to an intensity that it's actually going to burn out the pipework in the engine room, then it's going to render our whole fire main useless. So in that instance, if we're losing our seawater pressure through to damage in the engine room, then we can isolate that valve, and then we can still have our emergency fire pump supply the rest of our fire main up on through the decks on the vessel.
And covered from head to toe in protective fire gear is San Diego lifeguard Charles Davey. Davey is pouring gasoline on this boat, which he plans to set ablaze. Now, it may sound strange, not to mention dangerous, but it's actually a common training exercise conducted by lifeguards so they can gain experience in marine firefighting. an exercise that's done about 5 times a year. Only this time, it's different. Believe it or not, that's Charles climbing out of the boat. He's shaken, but alive.
Fire detection consists of our fire alarm panel and also our fire detectors. Alright, so our fire alarm panel needs to be powered by our emergency batteries so that even if a generator fails or whatever, we can still be aware of any potential fire threats. And it must tell us what zone the fire is in. And yeah, our fire detectors, they come in 3 main forms. We need to have a little bit of an awareness of each of those and probably be able to sketch at least several of them. So our main 3 types of detectors are heat detectors, smoke detectors and flame detectors. So let's have a look at each of those. So our fire detectors, our fire detectors smoke, thermal and flame, thermal being heat. Our smoke detectors are a couple of different types. One that uses a photoelectric cell, and they come in 2 types. We've got one that's got a light source and it shines the light directly onto the PE cell, photoelectric cell, and if smoke comes in, it impinges the light going through there and will activate the detector and send that to the alarm panel. Or we can have what we call the light scatter type smoke detector, which is a similar thing. It's just got the light source there, our PE cell, photoelectric cell, and there's a barrier in between. So ordinarily, no light can get through to the detector, the PE cell, and because of the barrier. But when the smoke comes in between the barrier and the PE cell, then the light bounces off the smoke and hits the PE cell and will signal the alarm. Or we can have another type of smoke detector is the ionization. So it uses a small amount of radioactive material, and then it has a reference chamber and a detecting chamber. It detects the smoke and sends an electrical signal through to the alarm circuit. Different types of heat detectors. We have a diaphragm here with 2 types of electrodes here. And when the heat fills this chamber in behind this dome, then the diaphragm is displaced and pushes the contacts together to activate the alarm. This is a similar one here. And another type is the bimetal. So there's a bimetal strip here which has 2 sets of contacts, which when the bimetal heats up, it expands and brings these 2 contacts closer together. This one too has a backup here in case you're wondering what this is. So this is another type that has, well, it's a secondary type, which if we get a rapid increase in the temperature, it'll melt this little fusible material, send this spring which will go flying up into the diaphragm and push on these contacts. There's our heat detector. And then we've got several types of flame detectors. One that tests or measures ultraviolet light within the flame with this gas filled bulb and electrodes. Or we have an infrared detector that again uses a photoelectric cell and sends electronically the alarm signal. We need to know how to draw several different types of detectors I would suggest two that are worthwhile learning is a smoke and a heat detector. For orals and examinations, this is important, and so I'll just show you. It's very easy to be able to sketch a heat detector. So I'll just draw a diaphragm here and a chamber underneath, and we just have several contacts, electrical contacts, and as this base fills up with heats up, then the diaphragm expands and brings the contacts together. We get an alarm signal, and then simply for a smoke detector, we can, with our ionization chamber, we have a light source here. This is a scatter type. We've got our PE cell, photoelectric cell, our barrier, light source, and ordinarily our light rays will not get past the barrier, but if smoke drifts through the detector, then we get random light scatter, and some of it will hit the photoelectric cell and give our signal back to our fire alarm panel. Testing of our fire detectors should be done as part of our planned maintenance system, so that all detectors are tested at least once every 3 months. And the way we go about it with testing a smoke detector, we can get artificial smoke, which is in an aerosol can, sometimes called smoke in a can. If you're really desperate, you can get a piece of bread and a cigarette lighter, and basically if this was the deck head and we had a detector, then we just get the artificial smoke can and we just spray it lightly across there, just very quickly, and wait, and then we can do that, repeat that again after a few seconds. Remember, there is a time delay to try and, so the system will try and prevent from having false alarms. It'll take a little bit of time to register. So we do a quick spray and wait, a quick spray and wait, and we do the same for our heat detectors, only we're going to use a heat gun, or you can use a hairdryer, but the same thing. We don't want to cook the guts out of our heat detector. We just wave the heat past it and wait a few seconds and do it again. We don't want to hold the hairdryer blasting on this detector, or we might destroy it. And then our flame detectors, we can test that by waving a torch in front of it just rapidly, and it'll pick up the motion of that light to test the alarm. Our fixed firefighting systems, they're fixed because they're in place, and we can use these to protect the accommodation on the vessel. Can be for cargo spaces as well, and for the engine room. So engine room fixed firefighting systems are what we're going to predominantly spend our time talking about. Accommodation services are generally protected with a sprinkler system or a water mist system. Generally they have a system that pressurizes it and has a total pressure charge on a water pipe system, and it comes to these sprinkler heads which have a liquid filled bulb in them, and when it has a temperature rating. When the temperature rating is exceeded, it might be 74 degrees Celsius, and if it exceeds that temperature, the bulb will break and this releases the water to start sprinkling. So unlike in the American movies where they all release at once, no, these will only release per bulb when the temperature is exceeded. The types of fixed fire extinguishing mediums that we have are water, inert gas, chemical, and aerosol. So I'll just give you some examples of each of these. Water is commonly water mists or mist decks. Can also use foam. CO2 is a common inert gas, but there's also inogen, argonite, chemical. A popular one has been halon, but also Novak 1230, FM200. Aerosols, a common one is pyrogen or NAFS 3. And it is worth mentioning a little bit about halon because this product is now banned. It still is in use and it is still commonly used, and it can remain on vessels if it's in place. It cannot be fitted as a new installation, but if it is released on an older vessel, then it can't be recharged. This has ozone depleting characteristics. All right, water mists. We'll have a little bit of a look at, but we're not going to go too much into the different types, but we are going to have a look at what they have in common in terms of releasing our system and how we need to prepare our vessel in order to safely and effectively release our system. Here's the basics of our water mist as a schematic. So here's a cylinder with our pure water, which is under pressure of nitrogen, and we have a release handle here which opens the valve to release this high pressure water through to these very fine nozzles. These have really fine nozzles like you might find on a diesel injector, and these are designed to release simultaneously and extinguish the fire. And here's a slightly larger system with multiple bottles stored under nitrogen pressure, or we can have ones with very high capacity pumps. And here's the difference between a sprinkler system and a high fog system or water mist system. And whereas this one has used 7,000 litres of water with 50% product damage, with the same fire using water mist, it only used 150 litres and only damaged 1% of the product. Alright, this is a CO2 system. This is for a cargo hold, but it's a similar thing for an engine room where we've got a number of sprinklers around the engine room via piping, and we have these banks of bottles, be they CO2 or halon or whatever they are, and these are outside of the engine room. And on smaller systems we have a cable pull release system generally, which releases down through and has to dump in a very short amount of time to try and extinguish the system. So look, that's the basics on our fixed system. Now let's have a look at how we safely go about releasing. I'm talking specifically about the release of our engine room fixed firefighting system. So whilst it's not our last resort option for fighting an engine room fire, it is one that we only have one shot at. So if we're going to try and extinguish a fire, we want to make sure that we get the right sequence and order to extinguish this fire. The first thing that we need to do is to muster. We want to account for all personnel. And in saying this, we talked about a lot of different products that we can use for extinguishing medium, and some safer than others, some claim to be safe, but essentially what I would say is that if we consider all fixed firefighting systems to be potentially lethal, to be asphyxiants, which means we cannot breathe in them, and to treat them this way, and we should be safe. So we want to make sure we're not going to release it with anyone down below in the engine room. We want to stop the supply of our fans. We all know the fire triangle and how that we have heat, fuel and oxygen. We take away any one of the sides of this triangle and the fire will go out. So if we can stop feeding with oxygen, then we're going to stand our best chance. And what goes with that, we supply our engine room with fans, but even if the fan stopped and we have ducting down to our engine room, then the air can still get down past the fan. So we have dampers that when they're released, it will come down and close that ducting. So fans, stop fans, close our dampers, and we need to stop our remote quick closing valves. Closing valves, some people call them instanter valves because they're sort of instantaneous closing. Our remote fuel quick closing valves. Okay, now who gets to say whether we release the system or not? I'm glad you asked. It is, of course, the master, because there have been instances where a system has had to be released with people down below, and also he's got to weigh up against any navigable hazards, because if we do operate this system, then we're rendering our vessel useless. Basically, we're going to be sitting dead in the water. Now, re-entry. When would we re-enter a space if we had released a system? They do say for ships, you're going to wait for 24 hours before entering with breathing apparatus, not trying to gas free. That's with breathing apparatus. Now, I would suggest that if you're on a coastal vessel, that you would allow it up, get in contact to allow firefighters to go in with breathing apparatus and determine that the fire is out. If you start vacating the space and introducing air to the system and it's not out, then the whole system could go back into flame again. I sometimes get asked about the question of, do you stop the engines if you're going to release the system? My answer would be yes, to stop your main and auxiliary engines. If you're going to activate your remote quick closing valves, then if we're shutting off the fuel, our engines are going to stop after some time anyway. So on small coastal vessels, we have emergency stops. So I would be stopping my main and auxiliary engines. Now, you need to know the steps to release this system. Okay, you need to commit these to memory. I'm sure you probably already know them anyway, but for exams, for orals, you need to know this thoroughly. Some vessel requirements, depending on the servo requirement, requires them to carry an international shore connection, which is basically a flange that is of a universal size. It connects to the couplings on your fire main, and this can be bolted to another flange that any other vessel or shore supplier firefighter can connect to pressurise your fire main. And it has to have this specific flange requirements, plus you need to carry 4 bolts, 4 nuts, 8 washers and 2 spanners to be able to connect it with.
I just want to introduce you to the fire control plan. Our control plan is placed on each deck, roughly around midships in the alleyways. They're often also placed in a cylinder that's close to either embarkation gangway, port or starboard. And this has all the relevant safety features of the vessel. So it has all the decks. So we start from the wheelhouse here, our forecastle, we've got main deck and the lower deck. And yeah, as I said, it's got all the safety information that we would need to know about the vessel, its location, how many. So for example, up on the bridge deck, we've got 4 life rafts, 2 8-person, 2 20-person life rafts. It shows you what position it's in, so I can go to just after the port and starboard bridge wings, and I would find them in that location. It shows us where life jackets are here, hose reels, our fire extinguishers. It shows us where they are in relation to major components on the vessel, such as stairwells, and shows an outline where bulkheads are as well, so we can find that sort of information. Moving down to our main deck, it's again showing us that orientation and where the items are located. So if we want to find a specific item, say a shutdown for ventilation, we can look in on the legend, find where that is. And so in this instance, we've got shutdowns. So these are all of our shutdowns here. We've got remote pump starts for fuel, pump stops for fuel oil, machinery ventilation space, remote stop. So it has this symbol, so we go and look for it on the fire plan, and it's not appearing obvious to me right now. Here's one of the shutdowns. That's it's actually a start for the emergency fire pump or main fire pump. So yeah, a lot of detail, a lot of information there, and as I said, they're readily available on all decks. But really it's not designed so that if we have an emergency situation we run and look at the fire plan. This is for us to study, be familiar with, so that we know the location and operation of the equipment when we need it. This is a reference point for us to be able to find out the information about our vessel and the safety systems that are on it.
I've been asked to talk about the life-saving appliances on board Bluefin. Now, up on the wheelhouse roof, which we call the Monkey Island, we have 20 life jackets in a float-free box. They're situated on the starboard side. We also have other equipment up there that we need to check, and one of those is the EPIRB. We've just come out of dry docking. We've replaced batteries, etc. in our EPIRBs. Also on the wheelhouse roof, the hydrostatic releases that are attached to the float-free box need to be renewed, and they've just been renewed. There's another 4 on board, and they're attached to our life rafts. Alright, we'll go for a bit of a walk around now, and we'll look at the various life-saving appliances that we have on board. So over here on the port bridge wing, we have our 20-man and 8-man life raft. They've just gone away for service. They're serviced annually. Hydrostatic releases have been replaced. Our life ring with smoke has just been replaced, and the expiry date on that is the 2nd, 2016. So up here we have our search and rescue transponder. Check the batteries on those. and you can see there the 4th 2014. Over here sitting on the table we have our line throwers, and we've just replaced the chargers in those. And for those of you that haven't had a look at these before, you can see the line in there, and the charge is actually located down in the centre of the line thrower here. It's a little bit stiff to get out. Anyway, I'll leave that one in there and I'll show you this one. Here's one I prepared earlier on. So it's a simple matter of undoing your line, pulling the old one out, pushing the old one down, and you can see it actually has a firing cap there in the bottom. Here's the trigger mechanism, and that's the safety pin. So once that safety pin comes out, she's good to fire. If we need to get a line to a vessel in distress, or there's a person in the water, and if the water was shallow and you couldn't take your vessel in there, you could potentially use one of these to launch a line over the top of the person. You definitely don't launch them at the person, and then they could potentially pull over a heavier line, and then you could recover them. Yeah, basically anywhere you need to get a line across to another vessel or person or life raft, etc. Very handy bit of kit. Over here we have our 12 para-red rockets. They're located in a watertight drum. That's your standard 12 para-reds. Expiry January 2015. So to keep track of all the appliances on board, what we do is we keep a monthly checklist. So that's our checklist there, and has every item on board the vessel, including the expiry dates. And as the mates go around and check the equipment, they can move into the month, and as they pass down through the vessel, checking the gear, they can tick off that it's checked. We've got our fire extinguishers throughout the vessel. So they're checked annually, and they've just been checked last dry docking. As per marine orders, regulations part 10, this vessel is to have a medical cabinet with all the various bits and pieces that we require at sea in case of an emergency. We have ours, we have a little bit extra in here, and we have a defibrillator situated in the bracket at the back there. Easy way to check that when you're doing the LSA checklist is to check the green lights flashing. As I've said before, we've just come out of dry dock, so all our medicines have been sent to the chemist, replaced and restocked. So she's ready for another year's operation. Full complement of life jackets are located within the vessel as well. So the things we check there is that the lights are working, and that there's a torch in the cabins. So each person has a torch and each person has a life jacket. So here guys, we have our full set of BA equipment. So you can see here we've got our torches, masks, cylinders, harnesses, spare bottles. This is a spare oxygen bottle for the Oxyviva upstairs. We've got our pressure gauges here. So as part of our monthly life-saving appliance checklist, we go through and check the contents of each bottle, and we put that in our checklist as well. And we've also got spare parts in there and a BA control board. On top of the BA cupboard we have our Paragard stretcher, and located throughout the vessel in strategic places we have our life rings. Some have lights, some do not. Starboard and port side in the A-frame. On the starboard side we have our emergency steering flat, and in the port side we have our emergency fire pump. Located port side down the vessel are our fire hoses. Each one comes with a nozzle and a hose key. Any two hoses should reach any one place on board the vessel. So we're down in the laundry now and we have our forward emergency escape. This is it here, and this actually passes up into the dry store, through the dry store, up onto the bow. This is our after accommodation emergency escape, and this one comes out near the main deck, near the aft door.
Okay, we're at the CO2 locker. This is a fire suppression system for the engine room. So if we get a fire that's out of control, we have got the option of dumping CO2, carbon dioxide, as a fire extinguishing medium. It will only extinguish fires in the engine room itself. And there's a few things we need to do before activating this system. Firstly, we need to muster. We need to account for all personnel because you cannot breathe while you're in the space when this is dumped. Okay, whoever's in there will be asphyxiated, so we need to muster to account for all personnel. And then we've got, because this is a one-shot system only, it's not exactly our last resort, but we only get to use it once. There's only one charge of CO2. So in order to make it effective, there's a few things we need to do. We're going to stop our engines. We want to isolate or stop our engine room fans. We don't want to be supplying air while we're trying to extinguish the fire. So we stop our fans, and along with that we want to shut the dampers. So while the fans are stopped, we can still get inflow of air. So we've got dampers which prevent the air from getting in even with the fans stopped. And then we've got our remote fuel shut-off valves. So we're going to isolate fuel to all the tanks. Often what goes with that is stops on any fuel transfer pumps, anything that can activate fuel in our fire situation. And once we've done that, then a decision is made whether to use this system or not. The decision to use it or not comes down to the master's authority. The reason for that is for several reasons. There have been and may potentially be instances where this system has to be released when there's people down in the engine room for the sake of the good of the benefit of the whole, of the safety of the ship and other crew members, passengers, etc. The other reason is that the master has got to weigh up, once this system is deployed, it's going to render our vessel inoperable for a considerable amount of time. And so he's got to weigh that up with respect to navigational hazards as well. Okay, so they're the conditions with which we need to release. We're going to have a look inside here. Once we open up this door, an alarm's going to sound, and it's going to sound in the engine room. It's very audible. It's also got a visual warning light as well. What I'm going to do is activate the micro switch on the door once it starts sounding so that I can stop it while I still talk to you. Okay, so we've got these door micro switches, so as soon as the doors open, it will start that audible and visual alarm, which we just heard. And then we have our banks of carbon dioxide bottles. Now, the quantity of bottles that we require as an engine room suppression system depends on the volume inside the engine room itself, and this is calculated and the number of bottles are then determined. The instructions for release of the CO2 system is very clear. It's labelled in this diagram, and it shows you the 3 steps required. The first is to open the yellow handle valve, which is this one, and that opens up our charge line to the engine room. Then we've got to pull, number 2 is pull the red toggle, which is this one. That releases a safety pin from here. And then thirdly, we pull the green toggle, which is this one, and that will activate this lever. Once that is opened, that's a valve that releases our CO2 gas into the line, but simultaneously it also provides an activation gas to operate each of these valves so that all of these cylinders dump at the same time. It's very important with CO2 particularly that we have the release happen in a very quick time, within 30 seconds. So This triggers each of the bottles to release into our main manifold to go down to the engine room and release all at once.
My name's Ashley, I'm engineer on the Bluefin. Today I'm just going to run through and explain our fire alarm and detection system on board the Bluefin. So our vessel is split up into different zones. So zone 1 and 2 is the engine room. Zone 4 is our lower accommodation. Zone 3 is our main access way off the aft deck, our galley, our mess, our workshop. And Zone 5 is crew accommodation. So if we have an alarm go off at any stage, the light will flash on here. If one of our detectors have gone into alarm, it'll flash, or there also is another light that'll also if there's a fault in the system. We can isolate zones, so if we want to do welding in the engine room or the workshop, we can isolate those areas so we don't set the alarms off. What else do you want me to say, Christian?
Yeah, I think that's probably about it.
Well, I can say, I suppose you're recording, you just edit what you want. Part of our monthly checks, we go through with our smoke in a can, and also we use heat for our other detectors, which are thermal rate of rise. So we'll go now and test one of our smoke detectors. So here's our synthetic smoke in a can and our smoke detector up here. So in our test, it's just a matter of shaking our can and applying some smoke into our smoke detector. See our lights flashing there? Hopefully it will alarm. Lights on, there we go. Upstairs, silence it. Alright, so that zone there, that was in cruise accommodation, zone 5. You can see the light here has come under alarm in zone 5, so we can tick that one off on our monthly checklist.
Yep, and then reset.
We can reset. Sometimes I like to leave it a while. If I reset it now, it'll probably alarm again.
Yeah.
So, just the smoke hangs around inside the detector.
Yeah.
So it might go back into alarm shortly.
So when we talk about engineering safety, engine room safety, there's quite a few aspects to it, but a lot of it is familiarisation with the equipment that we have on board, familiarisation with our safety gear, knowing where it is, so in an emergency we know what to do. Okay, we don't have to try and work things out, it should come more naturally. And part of that is testing ourselves. When we familiarise ourselves with a vessel, we continue to do that. You challenge yourself mentally, so you know the location and whereabouts, where extinguishers are, where the life jackets are, where the safety gear is, where emergency controls are, so that we can respond quickly in an emergency. Alright, also it's familiarising ourselves with systems, so knowing where systems are, where the pipe work is, and part of that is tracing. We might have system drawings on board, we may not, but we can lift up floor plates, grab a torch and follow where the pipe work goes, so that if we spring a leak, we know where pipe work's coming from and going to, and we can respond accordingly. A big part of operating a vessel is understanding the maintenance requirements. And we'll talk a bit more about that, about our planned maintenance, ordering of stores, that sort of thing, our logbook records, maintenance records. But a boat or a vessel is a bit like a farm. There's always something to do, and a big part of our job is to ensure that we do good housekeeping to make sure that there's not oily rags lying around. That we wipe up oil spills, we fix leaks, we have seals replaced or replace them ourselves, so that we operate a nice, clean and tidy vessel. We test our gear regularly. It should be part of our planned maintenance system, and it's taking pride in our job and what we do. We need to have a bit of an understanding of the SMS requirements for SMS, which stands for Safety Management System. This comes from an IMO code called the ISM code, which is the International Safety Management Code. And what this seeks to do is to focus on this aspect of it, because a lot of vessels may be required to have an SMS or safety management system, and this includes documented instructions for safe operations, and includes duties and responsibilities of personnel, and also how to go about reporting within the organisation, the company, and requirements for planned maintenance. So the operations basically will have a system that will explain exactly how to go about safely operating the vessel and its equipment, what all the navigation gear is, and how it can be safely manoeuvred, but also for engineering personnel, how to safely operate equipment, how to do start up and shut down of a plant, that sort of thing. So just to have an awareness that there is a document on many vessels that relates to safety management system, the safe operation on the vessel. There's a requirement for us to keep a logbook. There's a bridge logbook and an engine logbook, and this should be taken regularly with the readings that we have on our vessel, looking at pressures and temperatures of all our systems. Basically, if you don't have a logbook, it's easy to make one. You just look at for every engine and pump, anytime we've got a pressure gauge or a temperature gauge, then we can have a reading, and we can record all of these, and over time, if we have problems that we encounter, then we can see what the trendings are. So, if it was temperature, we're normally sitting about here, we can notice over time if a temperature is going up for whatever reason. Same with pressures, if we're starting to lose pressure. It gives us an idea of how we can look into that to fault find. Okay, it's when we're looking at gauges too, so if we have our scale, generally our gauges will run at a particular pressure or around a particular temperature. So if this is a typical gauge of where we have a running pressure, then I can get a marker and put a little mark here of where our normal operating temperature or pressure is. And it's very easy for me to see. As I walk around the engine room, I can see that, all right, it's in the normal zone. But get to know what pressures and temperatures that our machinery operates at, because then we can notice when things aren't going so. One aspect we've spoken about with in relation to engine room fires is that most fires occur when oil or fuel sprays onto a hot exhaust or a high temperature component. So I'm just going to have we're going to go into more detail with fuel injection systems, but if this is my injection pump, these deliver fuel pressure to our injectors. They're at high pressure, 350 bar or more. And this is called my high pressure injection line. This is my injector that's going to spray finely atomized fuel. And this is often a problem on our vessels. If we get a leak in here, as I said, it's very high pressure and it will spray fine atomized fuel all over the engine, hits a hot surface, and we get an engine room fire, potentially. So on a lot of engines, what they do is they double sheath the high pressure injection line. So we get another pipe which goes around the outside. So my fuel is only working through the center pipe. then we have a little line which goes to a tank called the leak off tank. It's a very small little tank, only holds a few litres, and then there's a little float that goes to an alarm switch. And if we get a leak in this inner pipe and fuel runs down and fills up the leak off tank and hits that alarm point, that'll send an alarm to our alarm panel, and we know to change this pipe and before it actually gets to become an engine room fire. Shielding the fuel is one way to reduce our chance of fire on board, but another way is through lagging and insulation. So any of the hot surfaces, if we can keep them from being exposed hot surfaces, then if there is a fuel or oil leak, then it's going to reduce the chance of fire. So I'm looking on the top of an engine, and we have our exhaust manifold. This is where our exhaust gas comes down. Most often we've got a turbocharger. I've just drawn one half of the turbocharger here, but because this is the hot side, the exhaust. So this is operating at hundreds of degrees, around 500 degrees Celsius. The gas flowing through our turbocharger, depends on our engine. And if we can lag this or insulate it, then we can reduce that chance of fire on board, and we can have soft lagging or hard lagging. And we can also water cool our exhaust manifold and turbocharger. But at any rate, we need to keep these high temperature surfaces lagged or insulated or cooled to prevent that risk of fire. One of the safety aspects we need to understand is that our engines can develop crankcase explosions. So we're going to look at a lot more detail in the engines, but I'm just going to draw the side of an engine, and here we have our crankshaft. So don't be too concerned if you're not fully understanding this system yet, but here I'm just going to draw a few pistons for a 4-cylinder engine, and we've got con rods, connecting rods attaching those. Oops. Draw my pistons at different heights. Okay. And then we've got on top, we've got the cylinder head with the valves. So this is called the bottom end, and up here now cylinder head and rockers is called the top end. Now on some, it is possible with our engines to develop an explosion in this region. The outside of this casing is called the crankcase. So we need to be aware that an explosion can occur if there's the right conditions. So what sort of conditions cause this? Well, firstly, we've got bearings in here and bearings in here. They're called main bearings and big end bearings. And so this shaft is rotating at high speed, and we've got lubricating oil lubricating all of this, our crankshaft. Now, if we develop what we call a hotspot, and this occurs wherever we have friction without the right kind of lubrication, we can get overheating in these bearings or in the pistons moving up and down inside the cylinder liners. Anywhere where we're getting a high amount of friction, then this can overheat, causing a part of the component to glow red hot. And when that occurs, we've got oil flowing through there that can cause the oil to start to mist, and then we can get this mist of oil vapor in the crankcase, which can be a potential explosion, source of explosion. So we get this mist, oil mist in there. We've already got our high temperature area, our hotspot, and this can be the source of the explosion. So we can get a crankcase which explodes in the right condition. So how do we minimise and reduce this effect? We have what we call crankcase relief doors. So here's an engine. This is the crankcase, this part here with our crankshaft moving through here, and this one has had a crankcase explosion. It's exploded part of the engine apart. Obviously it had no crankcase relief doors. So let's have a look at our crankcase relief doors or crankcase relief valves. So this is the side of the crankcase here, and this green part is the valve itself. So what we have is a lightweight aluminium type plate, and it's under spring pressure, and if we get pressure from our crankcase explosion, it pushes against this valve under spring pressure, opens up, and the crankcase pressure from the explosion can relieve, and there's actually perforations through this cover. This is to protect people from standing on the outside being affected by it, and there's normally a shield which allows it to relieve in the downward sort of location. Here it is here. There's an opening, comes down past here and normally down into the bilge type area, and because this is a lightweight valve, it closes very rapidly once the pressure is relieved. This is very important for this to be very lightweight and to close rapidly, because if it takes a long time to react and to close, then we may get an inrush of air which may cause a secondary explosion which is worse than the first. So these are crankcase relief doors. They're a lightweight valve which relieves pressure under a crankcase explosion. There are a few different ways to start our engines, and we can use electric starter motors, hydraulic starter motors. We can also have pneumatic air starter motors, or we can have an air start system. So this is one of those where we've got this is our cylinder head here, and we can have a valve that opens and uses compressed air to push down on top of the piston. So this is called an air start system or an air start distributor system, and we're going to talk about that because you can find that on some MD1 vessels, and there's some important safety things to note with this, because we can get explosions in our air start systems. So this is called the air start valve, and when we supply air pressure, it opens against spring pressure and allows air to come from here past the valve and to, as I said, push on top of the piston. So I'll have a look at the entire system and then some of the safety features associated. Okay, so here's more of a complete system. Here are the air start valves. They sit inside the cylinder head, and as I said, according to the firing order of the engine, it will push compressed air to get the engine turning over so that it can get fuel on and start. So what is supplying the compressed air to the air start valve is the air start distributor, which is this. It's a rotary distributor that turns off the camshaft. Oops. And so we have air from an air receiver or air tank which comes up through a starting air valve to the air start distributor, and this will rotate with the camshaft and it will supply air to each of these air start lines in the firing order, so that it starts pushing in the right sequence on these pistons to get the engine started. So we've got an air start distributor, air start valves, our main air starting valve, and our receiver. So there's another picture here which is showing our distributor here, our air start valves, and here we've got our This one's a solenoid operated start valve, but they can be a manually operated start valve. This is just allowing air to go through to the air start distributor. And it's showing our air receivers. This one's got 2, and then we've got a compressor, or 2 compressors. We can run one or the other to keep this pressure topped up. Now we need fairly high pressure to start engines with air, normally around 30 bar, between 20 and 30 bar air pressure. And here we've got a few safety items. So we've got a relief valve on the receiver, so that if this overpressurizes, it leaves air because it's a pressure vessel. We also have a drain, so this is very important on our receivers because we can get oil carryover from our compressors, and we can get these pipes oil coated. This is where an airline explosion can occur because we've got combustion gases potentially can get back through here and into the air start line. And so to prevent an airline explosion, first one we have drained so that we can drain off any of the moisture, including any of the oil residue which might form inside the tank. We have our relief valve. These should be a non-return valve. That should look like this so that we can't get any air back into the air receiver. So these are a non-return valve. We've got a non-return valve here, which is our isolating valve. And we've also got a relief valve here. And then one other component which they may have, I'll just sketch this up for you because it's not on the system. So here's a picture of our air receiver on our air start system. So these are the safety features we've got to reduce the chance of having a crankcase explosion. The first one is our drain here. We have a safety valve, which we talked about, which will relieve the pressure if it exceeds our normal operating pressure. We have a non-return valve on the outlet from our receiver, and we also have this guy, which is called a fusible plug, and it's just a plug which screws in to the side of the air receiver, and this will melt if the temperature exceeds above our normal operating conditions, and can relieve the pressure in the tank. And then we also have this guy, which is called a bursting disc, and basically somewhere on the air start line to the air start distributor we will have another pipe coming off that, and a disc which can rupture in the event of an overpressurization of, i.e. a crankcase, an air start explosion, and we'll relieve that pressure through our bursting disc. So we will need to have a basic understanding of an air start system because it is often asked in orals. So we should have an idea of the safety features relating to that and be able to sketch a basic system with an air start distributor. We're going to have a look at the IMDG code, or the International Maritime Dangerous Goods Code. This is a publication brought out by IMO, International Maritime Organisation. I'm using a fairly old edition, 2006. These are updated every few years, and but essentially the information is essentially the same. It might be a little bit updated in newer versions. So there's volume 1 and 2, and there's also a supplement. Now we just need to have an understanding and a bit of an idea on the IMDG code. Essentially, it tells us any chemical that we could potentially carry on a vessel anywhere throughout the world, and gives information relating to how it's packaged, transported, stowed, what it can be stowed with, how it has to be separated or segregated, and any of the emergency ways to deal with it, with fire, first aid, or a spill. Alright, so we're going to start with our book number 1, volume 1, And we're going to look at the hazardous symbols. You'd be familiar with at least seeing these plastered on the back of trucks. The HazChem symbols. So we'll just have a quick look at those. Here they are. And we'll just run through these quickly. So Class 1 for explosive substances. Class 2 for gases. Class 3 for flammable liquids. Class 4 HazChems, flammable solids. 5 is for oxidizing and peroxides. 6 toxic, infectious. Category 7 are radioactive materials. 8 fissile materials. 7. 8 is corrosive, and 9 is for miscellaneous. Okay, now one of the most important things that we have with the UN, with the Dangerous Goods Code, is the UN number. Now, this is essentially a number that is given to any potential chemical or product that can be classed as dangerous, and we're going to have a look at several products which may be useful for you in your assignment. So I'm going to look at volume number 2, and there's an index in the back that has pretty much any chemical in there, from his radioactive material, non-fissile, anything you can think of, propionitrile, potassium, phosphorus. Alright, we're going to have a look for 2 products. We want to research petrol and LPG, and we want to look at how we can safely stow them on board of our vessel. So I've got here petroleum gases liquefied, and this is a UN number 1075, and then I'm going to look at petrol, which is here as well. Petroleum products, petrol leaded. Here we go. And its UN number is 1203. Okay, so what I'm going to do now is look at petrol. I'm going to look that UN number up, and so petrol was 1203. Over here it gives me the numbers. It gives you the UN numbers on both pages of this table, and they're columns that go all the way across. We'll just have a quick look up here. This is the headings. So the proper shipping name, this is generically what the product's called, the UN number, type of class division, packaging, special provisions, intermediate bulk, containers, tank instructions, EMS, the emergency, firefighting, first aid or spillage, and then stowage and segregation. This is what we're going to be looking at particularly. And then properties and observations, so any particular information that we need to know about this product. Okay, so we're looking for our petrol 1203, and here it is here. So it says over here, motor spirit, gasoline or petrol, and has all that information. It's immiscible with water, so it doesn't mix with water, and it's in the category E, stowage and segregation, and we could look up FE and SE and find out about firefighting and spillage requirements. So we've got category E, stowage, and then we're going to look at LPG, which is 1075. Which is here, and we got petroleum gas liquefied, LPG, and we could look up about firefighting and spillage here. It says that it's flammable hydrocarbon gas from natural gas or from distillation of mineral oils, may contain propane, butane in various proportions, and it's heavier than air. Alright, Now it is also a category E, but it's got the extra clause here of clear of living quarters, so it cannot be in accommodation spaces. Alright, so next we're going to look at the stowage of these two products. So we'll look at category E. For stowage, I'm looking in volume 1, and I flip to chapter 7 on stowage, provisions regarding transport, and stowage category E tells me that cargo ships or passenger ships with not more than 25 passengers, then it can be stored on deck or under deck. So this is relating to both our LPG and our petrol. So on cargo ships or with less than 25 passengers, on deck or under deck. If it's a passenger ship, then it's prohibited. So we cannot have LPG or petrol on passenger ships with passenger numbers greater than 25. Okay, now next we're going to look at the segregation table, which is a bit further on. And so you can see here, segregation table. Now this is a handy reference which tells us basically what products can be stored with others. Now, and I'm going to look at, we've got flammable liquid, which is a type 3 hazardous chemical, and we've also got flammable liquids, which flammable gas, which is, our flammable gas is 2.1. If you look a bit further back, it's 2.1 for flammable gases, and we line up the two of these and we get a 2, number 2. Now come down here and it says 2 means separated from. So now we've got to go into the definition on the next page, which tells you it's away from, separated by compartment, blah 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 blah. And separated from, number 2, under the definition of the segregation terms, means this, that in different compartments when stowed under deck, providing the intervening deck is resistant to fire and liquid, a vertical separation in different compartments may be accepted as equivalent to this segregation. So what it's saying is they've got to be in separate compartments. If it's going to be between decks, then it has to have a fire resistant retardant deck and deck head. So otherwise they've got to be in different compartments. Now it also says for on-deck stowage, this segregation means a separation by a distance of at least 6 meters horizontally. So this is below deck. If it's on deck, it's got to be separated one from the other by a minimum of 6 meters. Okay, now, as I said, our supplement contains information on first aid and firefighting, but we firefighting, spills and first aid. There's also another form that if you are carrying dangerous goods of any kind as transported as cargo, then you need to utilise what they call a multimodal dangerous goods form. Now, I've got the wrong book, it's volume 1, and this is an example from the IMO that's given in the book, but AMSA has their own which they've developed from this form. So it's called the multimodal dangerous goods form. So any carriage of dangerous products, this form needs to be filled in and it needs to be submitted to AMSA. So there we go. There'll be an assignment on IMDG pertaining to the stowage of gas, LPG and petrol and the segregation of that and how we would interpret that on a problem on our vessel.